So to summarise that first part, you really have to think about your protocol design. You have to think about kind of perhaps using smaller steps to fit within our 8 to 12 minute top range, 8 to 15 minute boundary. You're looking for a plateau. That's the obvious thing that was coming out from all that literature I showed you earlier on with in this presentation, and that you have to recognise that the way in which you average your data that you're collecting has big ramifications in terms of the outcome of the test. Now what we're going to think about is, we've run the test, we've used a protocol that's fit within all those kind of criteria and those regulations. What's the outcome of the test? How do I define fundamentally the plateau? Because at the moment we've just been going, there's a plateau, it levels out. But we're dealing with biological data. It's perhaps never quite as clear as one would think. So this is some data, again from Adrian Midgley. This is a really nice paper. It's a shame there isn't more work in this area. And what he's done across multiple VO2 max tests, he's asked people why they have stopped. And this is important because we're making the assumption when we do the VO2 max test that the participant is stopping because they have hit the point of volitional exhaustion. They stop. We don't necessarily know at that point with our data whether they've actually really hit volitional exhaustion. We don't know straight away in our data whether they've hit a plateau. Because even with sophisticated breath-by-breath systems, they will not indicate robustly, certainly, that the plateau has been reached. You'll see the breath-by-breath data. You can make a guess, but you don't know. But notice what is interesting, that this is treadmill-based exercise. A large proportion said, well, they stopped just because they couldn't maintain leg speed. That doesn't necessarily mean they're at volitional exhaustion. They could struggle to make leg speed. That could be a neuromuscular fatigue. So we would need to be careful of that. They're suggesting here a large proportion that it's exhaustion, but then we get things like breathlessness and discomfort, start to get pain. So pain, again, doesn't mean exhaustion. So what we're starting to see as we go further down this scale is people are stopping for reasons that may not be a genuine justification for test termination. You have to allow the participant to terminate the test. That's generally the criteria that we would use. We have additional criteria on a cycloergometer. It might be that the cadence falls more than by 5 revs per minute, consistently falls more than 5 revs per minute. If it does without encouragement, we may then stop the test. On the treadmill, if they're slipping too far down the back of the treadmill, they're not able to accelerate up into a safe position, you'd always also stop the test. So they're clearly stopping for reasons that do not conform to what we're thinking about, which is volitional exhaustion. And this then has ramifications. And this is where the idea of having some way of ascertaining whether a max effort was given is really important. And this is where the idea of our VO2 plateau comes from, or stems from. So this is from Dave Paul and Andy Jones, published in 2008. And this really starts our little discussion here. In the classical literature, the VO2 response is depicted as an increase in VO2 as a function of work rate up to the achievement of VO2 max, after which a VO2 plateaus despite further increments in work rate, as shown by Aston in 1960 and Hill in 1923. Which is what we've shown, in all those images previously. So that is the classic response. And so if we see that in the data, irrespective of actually what the participants indicate here, if we've got the plateau, we are by definition at max cardiac output, max AVO2 difference. We are at the point of volitional exhaustion. They're relying on anaerobic metabolism to maintain exercise. They cannot use any more oxygen. So it makes a lot of sense. But they go on to write this. This is a paper that we published about the plateau. A VO2 max is typically confirmed by the presence of a plateau or levelling off in VO2 despite a continuous increase in exercise intensity. So we're kind of confirming what you see from the Paul and Jones paper, and it is absolutely what is done. Now the question is, how do we define a VO2 plateau? Now what is this about? Well, if we give ourselves the rationale, again, this is perhaps reinforcing some work. This is again from a paper that we published on this. The physiological rationale for the plateau in VO2 is that during incremental exercise, as we've already reported this, an imbalance starts to occur between the supply of oxygen to the engaged muscles, as expressed by the cardiac output, and the extraction of oxygen within the tissue or the muscle, as characterised by the arteriovenous oxygen difference. At the point of volitional exhaustion, Q rises to its maximal value, and there is a concurrent levelling off in the AVO2 diff, with the response in Q being attributed to an increasing heart rate and a continued rise in stroke volume in trained individuals. In the untrained individual, the stroke volume will leveled out actually at about 50 to 60% VO2 max. But all of those point to the fact that we cannot deliver or extract any more oxygen per beat of the heart. We're relying on anaerobic metabolism. And the issue is this. As much as the classical response that one would anticipate to see is a plateau, which is what we see here, it is not typically what we see. In fact, there was really good data from a paper published by Mike Doherty back in the mid-2000s, which suggested actually that the response rate was anywhere between 0 to 90% of participants. So quite often participants will not produce a plateau. Now, is that because they've stopped because of fatigue, or is it that they can't produce a plateau? And if they produce one of these other responses which we typically see, are these still a max effort? Because if the VO2 isn't rising, as you see here, this is what is typically referred to as VO2 peak. And the problem with using the term VO2 peak, as you're about to see, is it actually does an enormous injustice to the data. Because the problem is, you wouldn't know whether they're at max cardiac output or max AVO difference unless you're recording that data simultaneously, which excuse me, becomes quite invasive and demanding on the participant. We may do that clinically, but we certainly don't do that in athletic population groups. And what about this group? This is an interesting response. The VO2 starts to level out, then drops off. So if we are doing that averaging, and we're averaging across our last few workloads, what do we do here? Well, do we call this the VO2 max? But the workload is increasing. What's going on here? So this one quite interesting. And this one's easier to explain because it perhaps aligns with this one. What about this group here? These are quite unusual. These are what I call accelerators. So the VO2 rises incrementally, looks like we're plateauing, then accelerates again. And again, the same thing applies. If I'm using kind of averaging, let's say I'm doing, taking an average, I'm looking for the difference across these workloads, then the VO2 is rising. Is that a VO2 max? Because the definition is that the VO2 should be leveling out. So it becomes more interesting when we start to think about, well, okay, how do I define a plateau? And this is where an awful lot of miscommunication, misunderstanding comes from within the literature and within applied practice. And it really stems from this paper and actually an earlier paper which was published in 1955 by Taylor and colleagues. In the Taylor and colleagues publication, they used this criteria here. And this criteria here is that they used a cutoff to define a plateau of a difference of less than 150 mil per minute increase between the last two successive data points. So if the difference is less than 150 mil per minute, then that was defined as a VO2 plateau. Because we get biological variation. A number of things to understand is, well, firstly, where does 150 mil per minute come from? Well, in the original Taylor paper, and as has been to a degree replicated here, the argument that was made was, well, you've got to come up with a way of defining the plateau. You can't just simply go at its level, because that's eyeballing the data. So what they looked at was what was going on submaximally. And so they looked at the submaximal response. And remember that the VO2, as we defined previously, increases linearly, or has a linear-like response to exercise intensity. So you could work out what the average VO2 response was. So in this data set here, they've worked out the average VO2 based on the slope is 300 mils per minute per every 2.5% increase in gradient. So the net result was that Taylor recommended, and as Howley and Bassett have done here, was, okay, they worked out, well, half of the difference, so fundamentally if it's slowing down its rise, which is a plateau, if we go with half of that, we define that as a plateau, hence 150 mil. But herein lies the problem. That protocol, that method has been adopted across institutions globally without understanding where it came from. This response is based upon the protocol. If I use a 1.5% increase in gradient, I don't get a 300 mil per minute increase. I might only get a 250 mil per minute increase. Therefore, my criteria isn't 150 mil, which most groups use. The criteria is 125 mil. But we want to go a stage further. And you'll see why this becomes relevant as we get towards the end of this presentation, which is, I mentioned a moment ago, understanding the individual. You can't arbitrarily adopt the same criteria because you've used the same protocol with everybody. Each person will react differently. They will have a linear-like response in terms of VO2 to work rate, but will react differently. So even if we use this 2.5% increase that you see here, one participant might have a 300 mil per minute increase, one participant might have a 200 mil per minute increase. They need to have individualized plateau criteria. And so the net result is, where this has been adopted, and there is another version which is out there, which is 2.1 mils per kilogram per minute, which when one looks at it, where did it come from? Well, it was based upon the Taylor data, where they just normalized the data for their participants to body mass. It was 2.1 mils per kilogram per minute. So groups have adopted that as a criteria. The issue is they are not standardized to the population that you're working with. They have to be standardized to your participant and the protocol that you're using to ascertain that it is a VO2 max. Now, where it becomes very interesting is, imagine if you've got two successive workloads and you've got the data. So here it looks like it's rising, but if the difference is less than 150 mil per minute, it falls into the plateau. What about if it's going the other way and it's falling? The difference is still 150 mils per minute. Is that a plateau? So it's not as perhaps clear cut as one would think, but I think the really important take home message is, you cannot have a fixed criteria across everybody. It has to be individualized, and it has to be individualized based upon the response. And so that may well explain why in the literature a lot of groups are reporting these large discrepancies in the number of individuals producing a VO2 plateau, because they're using a generic criteria to identify the plateau-like response. And you can see here, so here we've got some data. This is from a paper we published back in 2012. So here we've got, in this example, actually we did time averaging, which moving forward, we've moved away from time averaging, but you can see what's going on. Here's the final minute of the test, and you can see here the VO2 mils per kilogram per minute. This is, a lot of data. These are all breath by breath points. So here's a plateau response, absolutely, level in terms of what's going on. The others may well be plateau responses depending upon what the criteria is I establish for the levelling out. It looks like, particularly in this example here, this looks like it's really rising across the course of the test. But unless I know what the individual response is based upon the sub-maximal data to establish what the increase is per stage, I can't absolutely be certain. I think for this one I could be certain because you can see it's absolutely level. But the others we don't know. Now, why did I say earlier on that we need to think about this in terms of the individual? This is a paper we published in 2020, and which was one of the questions we were asking was, okay, let's make the assumption that we've used individualized plateau criteria. And we've used individual plateau criteria and we look at the data. We still start to see that some people, despite that, do not produce a plateau response. And you can see two individuals here. This is classic plateau response. Here's the breath by breath data. You can see the average response in the middle. In this individual here, who we've got an individualized criteria for, the VO2 is still rising. So there's clearly something else going on underneath, and in spite of actually standardizing our criteria. And this is where we started to ask the question, which is it down to the individual? And actually it is. The ability to produce a plateau is dependent upon our ability to work anaerobically. Remember that at the point of VO2 max, we're making the case that cardiac output is maximal and AVO2 difference is maximal. Therefore, we have to be working anaerobically. So what we've done in this study is we've screened our participants genetically, and we've looked at the way in which they express key genes. And if we simply dig into this data, and what I want you to look at is just look at the top 3 genes here. So this is actin 3, ILF, and this third gene here. These genes are all genes which are related, particularly our actin 3, to anaerobic substrate metabolism. If we come further down, and we've got to come right the way down here, this is PGC1 alpha. PGC1 alpha is one of the key aerobic genes. It's often the gene that is used to identify aerobic capability. You'll notice that it is not at all associated with the ability to produce a plateau response. So there really is a great indication here that the ability to produce the plateau is genetically linked. So it poses a problem. If the individual cannot produce a plateau, despite the fact we viewed the individual criteria, they fundamentally aren't able to produce one, how do we know they've given us a maximal effort? Because remember that the plateau is our primary mechanism of identifying that max effort has taken place.